Welcome to my JuliaCon 2021 talk. My name is Churavy. I'm going to talk about Enzyme.jl, reverse mode auto-differentiation over LLVM IR. When we talk about auto-differentiation in Julia, there is one question. Aren't there just enough AD frameworks already? For forward mode auto-differentiation, we have forward diff.jl, which has been very popular and very successful. And for reverse mode, we have a whole slew of different packages. Reverse mode.jl is, I think, one of the first. Psycho.jl is one of the most widely used ones, especially for machine learning application. Kino Fisher recently introduced Diffractor.jl, which is a new ID toolkit. Invinia has its own Nabla. Flux used to have its own Tracker.jl, and KNet has AutoCAD.jl and Yoda.jl and Nilang. And that, I think they're even more than that. So what does Enzyme bring to the table, and why do we want to use it for auto-differentiation in Julia? Well, first of all, Enzyme is language agnostic. So Julia is a programming language that emits LLVM IR, and we use LLVM to drive our code gen and optimization. Enzyme operates over that LLVM IR, and it can be part of an optimization pipeline. So I can do some optimizations of my code plan first, then run Enzyme, synthesize my gradients, and then run additional optimization passes that will then co-jointly optimize the gradient as well as the formulas. Additionally, and in contrast to other AD toolkits in Julia, Enzyme can handle mutations efficiently. So both mutating something like a mutatable struct or an array allocation will work, and the user does not have to change any of the user-facing types. So it doesn't face the problem of a few of the auto-differentiation toolkits in Julia, where you have to either write type-agnostic code, or you have to permit the change of type to something that is the internal type of the AD toolkit. It also supports synthesizing gradients from GPU kernels. Both CUDA.jl and ND-GPU.jl are supported, and I'm going to demo one of those an example with kernel abstractions at the end of the talk. Furthermore, there's ongoing work with G-Shot students and collaborators to support differentiating through MPI, class operations, and foreign function interface. So if you're calling a C library from Julia and you want to differentiate through that C library, you can use Enzyme to do so. Additionally, it's very fast. By the virtue of being able to run post-optimizations, Enzyme can synthesize significantly faster gradients than other tools. So, as I already described a little bit, the Enzyme approach is really operate over the optimized code. And there's a little bit of a caveat there. The question is what does the optimization do? So some optimizations are platform agnostic, and they make the code simpler and easier to understand and reason about. And then there are platform-specific optimization, that as an example, the vectorizer in LLVM, which will make the code run faster on a specific platform, but also harder to reason about. So ideally, we run enzymes after we have done serious optimization in LLVM, and then furthermore, then do the platform-specific optimizations. If you want to know more details, William Moses described quite a few of them in one of his talks about Enzyme. And this leads us to one of the main challenges of Enzyme. We are going to do auto-differentiation not over high-level Julia code or the Julia IR, but we are going to do auto-differentiation over the LLVM IR. And quite a bit of information has been erased by the optimizer and the compiler at that point. So, as an example, if we take the C function f, which is just a mem copy from a destination array to a source array, and dependent on the type of the data we are passing in, we will have to synthesize different gradients. And that is due to the fact that float and double have different sizes of how big the elements are. And so the semantic information must be preserved that we are operating over floating point elements of size 32 or size 64. So in order to solve this problem of being able to differentiate over low-level code, especially where type information has already been lost, or types are no longer semantic meaningful, but have platform-specific meanings. So in LVM, the types correspond to register types and not necessarily to the original semantic types in the program. We have to run type analysis, which will reconstruct the types on the LLVM level. And in Enzyme.jl, we prime this type information with what Julia knows about your program. Then the next important step we're doing in Enzyme is we perform activity analysis. So we look at your program, we look at the activity of the input arguments, and we determine which instructions in your program are relevant for the gradient calculations. And only those will then partake in the backward pass, and that greatly simplifies what we need to do with. Enzyme uses shadow memory as a way to store gradient data. So if you pass in an array, if you call Enzyme, you will also have to pass in the shadow of that array, which is an array of same size. Or if you're passing a mutable struct, you have to pass in a shadow of that mutable struct. And that memory is going to be used to perform the gradient updates. Lastly, there's also a cache. So Enzyme can operate in two different modes. One of them is a combined forward and reverse pass, where we run both the forward code and the reverse code in one function, and you, as your output, you receive both the result of the forward and the reverse pass. But you can also do a split mode. And so you can have an augmented forward pass where Enzyme will insert additional code that will maintain a cache and carry data between the forward and the backward pass. And then that cache will be used by the backward pass to then calculate the gradient. So to make these concepts a little bit more clearer, let's talk about these things in detail. So type analysis and interprocedural data flow analysis. So if you're familiar with Julia's type inference algorithm, that is quite similar in the underlying notion, but we're, instead of figuring out Julia programs, we're trying to figure out LLVM IR. Each value is described as a set of memory offsets and a type annotation to those memory offsets. And we, in the end, will perform a fixed point update. So we will use abstract interpretation to establish a type through the program. So let's say we have a mutable struct, my type in Julia. It has a float64 value and then a data, which is a raw pointer in this example. We will represent that as a pointer itself because the mutable struct, and at offset 0, and that will point to at offset 0 a float64, and at offset 8 a pointer of integers. And if you put on the debug information, you sometimes get printing of these nested structures, and this is basically saying encoding the same information. As I mentioned, activity analysis determines what instruction could be impact derivative computation, and it has two side effects. One of them is there are not differentiable operations. As an example, CPU ID is not differentiable, and defining what it would mean to differentiate it would be impossible. So an instruction is active if and only if we can propagate a differential value to the return of the function or some memory that is the output. We use alias analysis, which is a set of LLVM analysis passes, and type analysis, which is enzyme specific. And as an example, read-only functions that only return an integer and inactive, since you cannot propagate any gradient information through those functions. Most auto-differentiation frameworks have some notion of a tape. In Enzyme, we decompose these notions. So we have the shadow memory where we'll store the adjoints. we have a cache where we record data necessary to perform our computations for the gradient. And when we synthesize our reverse pass function, we will record this information, and that is a purely static operation. So in contrast to AD frameworks, as an example, in Python or early ones in Julia, where the tape was also the tape of operations. This allows us to reduce the overhead per operation significantly. The additional benefit is because we generate the reverse instructions directly in LLVM, we can also annotate behavior for optimization, generate better code. And if you're more interested in details, the paper is on arXiv or in the new IPS 2020 proceedings. Right. Shadow memory is, as I mentioned before, is a derivative of values, and we store those in the shadow allocations. For all active values, you need to allocate either Enzyme or the user need to allocate and zero the shadow memory. And all data structures need to have a shadow memory. And we will get to some interesting ones later on. And Enzyme will manage those sometime itself. And if you're passing them in as arguments, you will have to also pass in the shadow. So that is the constraints being put upon the user. Some operations, sometimes calculating the adjoint will require to forward values from the forward pass to the backwards pass through the cache. And so, as an example, if I take the gradient of the multiplication between two values, depending on which value I'm differentiating with regards to, I might actually need the concrete value of x that was used in the forward pass. So I will need to store that in the cache. Right. Another thing that is solved through the cache is how to deal with dynamic control flow. Especially loops are tricky because we don't necessarily know how many iterations a loop will take. And so we will store, first of all, the number of iterations taken, but we will also store values that are computed if necessary. If you used Enzyme.jl previously, you might have noticed a couple of limitations. Firstly, the Julia functions you wanted to differentiate could not allocate any memory, and they could not use any dynamic function calls. And so we fixed the former by moving Enzyme earlier into the pass pipeline before the late load GC pass, and by defining the appropriate definitions for object allocations and array allocations in Julia. Secondly, we now have experimental support for dynamic Julia programs. And so we have custom gradients defined for GL applied generic and its friends and families. And when you have a dynamic function call within your program, we will execute that function call, and while we do so, re-enter Enzyme.jl as part of the chitting process, and start afresh from there with the type of information we have and differentiate your program from that point on forward. And so every dynamic function call will hit Enzyme.jl again, look up the right definitions, generate and synthesize the right code, and then carry on. We also added support for user-specified activity on the return value of a function. Since Enzyme 0.6, we stopped using cassette, and we are now performing known function mappings, think sine, cosine, at the LLVM level, and this greatly improves the quality of inferred code, because in cassette.gl messes with the code a little bit too much and enables us to differentiate more functions. I talked before about activity information, and we allow the user to specify that. So as an example, const, active, duplicated, and DuplicatedNoNeed are web structs that you can use to around the argument to a function to be differentiated, which will help Enzyme to make decisions about the synthesis of the gradient. So const means that the argument is assumed to be constant and will not participate in gradient calculation. Active are scalar or immutable values that we want to differentiate with regards to, and the gradient is propagated through the return value. Duplicated are mutable arguments, so arrays or mutable structs, and they take a second argument, which is the shadow of that argument. DuplicatedNoNeed is like duplicated, except that Enzyme will not, can assume that the original result, the val, is not necessary. And so that makes code cheap. If you have inputs to the forward pass, you will want to allocate a zeroed out gradient, a shadow. And if it is an output to the forward pass, so as an example, if you have a mutating function and you want to calculate the propagated gradient from a previous step in, or you want to calculate the gradient with respect to the argument, you will either want to take the previous gradient or fill the shadow with one. So enough talking, let's do some live demos. So I'm going to demonstrate, first of all, the activity annotations. So again, we have const, we have active, we have DuplicatedNoNeed. And let's start with a very simple function. So this function square will calculate the square of x. And we know that we would expect the gradient of this to be 2. Now, when we call Enzyme exports a function called autodiff, and that function takes in the arguments and the function itself, and then will calculate the gradient with respect to that. The default activity for all values is const, and therefore we see that we receive an empty tuple, and that empty tuple means there is no gradient being calculated. Now, if you set the argument to active and you propagate the gradient in, well, then you will actually receive the gradient of 2, and we can, of course, change this, and we will get the correct gradient result. Now, as I said, new in version 0.6 is that return values also have activity. And so this, if we set the return value to have a 0 constant activity, we will get the result 0 in this case, because we told Enzyme explicitly that we do not want to have the gradient with respect to the return value. Now, as I mentioned, Enzyme supports mutating functions, and let's take a very simple one where I pass in y and x as references, and I calculate the cube of x. And so as an example, here is how I would call this function in normal Julia. And so if I want to calculate the gradient of x, we have to propagate 1.0 into the shadow of dy. And so I'm going to allocate the input arguments, and I'm going to allocate the shadows, those input elements. And then I'm going to call duplicated of the inputs and pass it in. And as we can see, indeed, we are calculating the gradient with respect to the input. And so when we start changing this, as an example, right, if I change this to 2, you see that we are now, we are actually multiplied the, Enzyme will multiply the value being propagated in with the gradient of the function. So that's why I need 1, because if I put in 0, well, then my gradient with respect to that is also 0. So DuplicatedNoNeed is the same as duplicated, except that we do not compute the results necessary for the actual output, in this case, y. So as you can see, y is actually set to 0. And previously, it was indeed 64. Now, there is reflection utilities in Enzyme itself, so Enzyme code LLVM and code typed, where you can pass in the function and all of its arguments annotated as you want it to, and you can look at the LLVM IR being generated. And I'm going to skip over this in the essence of time, but basically if you look closely, you can see which instructions we did not have to create if we use DuplicatedNoNeed. Okay, so one of these examples that Billy showed me very early on, which I found very interesting, was actually differentiating through control flow. And so this is something, especially for scalar code, where you would traditionally in Julia use forward.diff.gl, and you would normally not use any reverse mode auto-differentiating tool like Zygote, because those have unacceptable overheads. So as an example here, this is calculating the Taylor series, and we are going to have a loop that is updating G for 10 to the 7th number of steps. And so we can use Enzyme to calculate the gradient of this quite quickly. And then let's define 3 different functions that use 3 different auto-differentiation frameworks, forward diff, Zygote, and lastly, Enzyme itself. And if I benchmark this code, I will see that a forward diff takes roughly 1.3 seconds. In the minimum, and where if I use Zygote, it takes 35 seconds, and it allocates a lot of data. And this is part of a design decision on Zygote's part to really focus on machine learning workloads and array-based codes, and therefore it does not perform well on scalar codes. Enzyme, in contrast, performs the gradient calculation in 6.97 milliseconds, which is roughly twice as fast at forward diff even. Now, these codes so far have been fairly simple, but Enzyme can also handle more complicated codes. And as an example, I'm going to use a matrix multiply. So this is a standard matrix multiply. It's not the most optimal one, but it's a good starting point. And so again, we will generate some random inputs. We will then allocate the return value. We will create the gradient. We will allocate the shadow memories, and so some random data passed in as an example here. And then we will call autodiff with mymul as an argument and duplicate it for all of the arguments. And so we can then confirm that indeed the results are what we expect. The result is approximately the matrix multiply of A times B. And if you look what the definition of the gradient of matrix multiply with respect to the different arguments are, these are the definitions, and the answers are also correct, and the performance is reasonable. Now, this was some mutating code that is already difficult enough to deal with, but as an example, we can actually take much more interesting, fun code where we, as in this is an example of a linked list that I wouldn't initially have thought is Enzyme will just be able to differentiate through. But indeed, basically what we're calculating is the sum of all of the elements in the list. And so again, we create the regular and we create the shadow of the linked list, which is a copy of the same with all of the data elements to 0. And then when we calculate the gradient of sum list, we can find that indeed the shadow of the sum operations are stored in the right locations. And that's kind of the magic of Enzyme. I can take arbitrary codes, I can throw at it, and it will figure out the meaning of the code based on the low-level semantics. So it doesn't need to know anything about LList. It just knows the meaning of the memory operations that you're performing on the LLVM IR. So The other demo I wanted to do was to show this on GPU codes. And so this is a matrix multiply example using kernel abstraction. I also showed this in the Julia GPU workshop. And so let's skip to the definition of the function, and it looks very similar to the matrix multiply we just looked at. And we allocate our inputs, and then we first check that indeed the result is what we would expect. And in order to take the gradient of this code, we, instead of calling autodiff with all of the with the function itself, we can use a work in progress package called kernel gradients, which defines an autodiff on the kernel object itself. So we instantiate the kernel for the right compute device, and now we can allocate the shadow memory, call the new kernel that we just created using autodiff with the duplicated arguments on the host side, and indeed we will get the correct outputs here. And this is kind of amazing because we're doing memory operations on a parallel device on GPUs, and Enzyme.jl knows how to deal with parallelism on the LLVM level. There's a paper coming out for supercomputing that details more about how Enzyme handles parallelism. So what is next? Well, we want to stabilize dynamic function call support, so please send us your issues, try it out, and tell us which codes don't work yet. I also want to make it easier for Enzyme to be used to differentiate through foreign function interfaces. So if you're calling a C library from Julia or a Fortran library from Julia, you should be able to use Enzyme to differentiate through it, but we do need the LLVM bitcode to be available for that library. So maybe we can add support to Yggdrasil and Binary Builder to automatically compile and cache the bitcode for the library and then look it up in Enzyme so that that will be seamless for users. I also want to improve the ChainRules integration. Right now it is possible, but it is rather clunky, and we are missing a couple of features. Also, split mode, so the process of calculating the augmented forward and the reverse pass separately from each other is currently not exposed. You can only use the joint mode. So we want to provide a user interface for actually using that. And I want to publish and stabilize kernel gradients, which gives you automatic differentiation for any kernel abstraction-based kernel. So some of the wishes we have for the ChainRules.jl interface is to be able to reason about activity information. And the challenge for Enzyme is that we do need it already at the forward pass. We can't just have it at the reverse pass. And this is necessary, as I mentioned, to reduce caching and to only compute what is needed. We also would like to have better support for declaring that a chain rule is supporting mutation or in-place gradient accumulation. Right now there is this thug interface which allows you to do in-place gradient accumulation, and some variant of activity propagation, but it happens too late. We would like to do it earlier because we are going to synthesize the code accordingly. We would also like to use chain rules to actually add higher level rules to the low level rules that Enzyme is already using. But we are having a challenge that if you're inlining functions during the forward pass on the Julia level, we cannot use chain rule to then look up what the function means because the function doesn't exist anymore. It has been inlined. So maybe we can work together with the Diffractor to actually define a pass to expose, to say, well, do not inline these functions so that we can then later on use chain rules. So alternatively, one of the more clearer examples is that if we encounter dynamic functions, we might actually just want to look up if chain rule already has a definition for that function and use that instead of re-entering Enzyme. So To summarize, Enzyme is a tool for performing reverse mode auto differentiation of statically analyzable LLVM IR. And as we've shown, that statically analyzable is expanding with language-specific extensions. So in Julia, we can now have dynamic calls supported as well. It can differentiate codes in a variety of language. So C, C++, Fortran, Julia, Rust, Swift, and everything else that targets LLVM IR. Depending on the complexity of the language, you will have to add language-specific knowledge to it. It has state-of-the-art performance with existing programs, so no need to change the code. It can handle mutation and GPU code. And it supports cross-language ID. So in theory, you can start in Julia and end up in Fortran while visiting C. So please give Enzyme.jl a go. It should be as easy as installing it with a Julia package manager. And please feel free to open issues, open pull requests, contribute to either Enzyme.jl or Enzyme proper. And I look forward to interacting with you on GitHub.